Okay, hello once again, everybody. Not too much people are here, but let us start. I wanted to recall what we have seen yesterday, but well, if you have any question, we can go back, but otherwise. So we have seen the empirical pseudo-potential method yesterday, and after that, density functional theory. Well, some applications about alloy system. How can we have the band gap for semiconductors, and we spoke a little bit about also metals, about CPE method, VCE, virtual crystal approximation for semiconductors, and the model of Bernard and Zunger. How can we calculate the band structure, and of course also the density of state, the electric function, everything relates to energies. And we said that from going from empirical, which is based on the knowledge of or the fit of potential parameters to experimental data, going to ab initio, we have accuracy which increase, but the price is the complexity, because we have to it's more time consuming. We have to take less number of atoms, because we have much more interactions between the electrons, ion, and so on. Density functional theory, we spoke about Kohn-Sham equations too much. Okay, the little bit history and how can we modelize. Okay, we start with this adiabatic approximation, and after that we spoke about the major problems, electron-ion potential. Okay, and then exchange correlation. Well, for electron ions, some examples here. Well, this was a resolution of the Kohn-Sham equation, and the major problems, exchange correlation and electron ions. From here we have several approximations, I said. Local density approximation, LDA and GG as well. The example was given for LDA. How can we approximate this exchange correlation with these equations? We saw them from Perdue and Zunger as parameterized by Sepperli and Alde. So concerning the electron-ion potential, we spoke about mainly about pseudo-potential method, and we said that this is constructed by a pseudo-potential, so weak potential, with some improvements during the several years from 1970 and so on, and with the plane waves. Okay, we have strong oscillations inside of the Hertz region and plane wave outside of the curve or Hertz region. Okay, and we spoke about the need to use sometimes a great number of plane wave if we want to describe the strong oscillations. Okay, the introduction of pseudo-potential, the main idea, and we want to this figure where we see the pseudo-potential. Okay, which will replace the strong and deep potential inside of the Hertz region, the closer electrons, and the pseudo wave function, which is rather smooth when you see on the top side. Okay, and well, here how to construct pseudo potential. I gave some the equations, and after that some examples. The main potential used, Hamann and co-workers in 1979, DC Physical Review, Zunger and Cohen during the same year, and then Kerker, it was published in Journal of Physics and Matter, Bachelet, Hamann, Schluter in 1982, Physical Review B. They make a table for all elements in Mendeleev table for showing pseudo-potential, and after that Shirley and Vanderbilt in 1992. So the main thing to remember is that we need before constructing potential, to have as small as possible number of plane wave, and we should take care about the transferability of these potentials. Okay, so when in principle, if the pseudo potential is good for a given atom, it should be transferable to any other system of. Okay, so, for instance, I gave the example of zinc. I can use the one of zinc to study zinc as a metal, but also zinc in combination with selenide as semiconductors and with another element, for example, with oxide as ceramic and so on. And I don't have to change this pseudo potential according to the situation. No, this is transferable pseudo potential. This can be used for simple molecules, solid, and also the other systems. Some other remarks concerning pseudo potentials and the total energy here, and we said that the diagonalization of the matrix it makes it difficult sometimes because we have to reduce the number. Let's say, the number of glasses I have. So, the number of atoms. Okay. Since some students just come, I will be a little bit more slow. I will repeat a little bit what we have done yesterday in 10 minutes, okay? And then we can go further just to, gracias. You know that I drink too much water, yeah? Okay, let me back to here just to give you an idea about this. We'll use 10 minutes more, maybe, but for this. Okay, we'll go here a little bit fast, but just to explain you. So, right now, you know, since last week and the first session this week, we spoke about atomistic methods, as I said. So that means that we consider the atom as rigid, and here we are going to speak about quantum methods. So the smallest quantity will be the electron, not the atom. There are a lot of methods. I will start with empirical, like empirical methods for the atomistic one, for molecular dynamics. Here we have some other empirical methods, like pseudopotential method, tight bending, okay, and so on. Okay, let me give the example of empirical pseudopotential, and we will see that there is also ab initio pseudopotential. So, what means the pseudopotential? The term or the name pseudo means almost. As I said yesterday, we can say use this for everything. This is I don't know, pseudo color, pseudo person, pseudo work, pseudo president, if we want to make something funny and so on. So this why this is pseudo? Because this is not a real potential. If we see here this system silicon, you will see that we have 10 electrons which are close to the nuclei. Okay, 1s2, 2s2, 2p6, and 4 electrons which are outside. Okay, they are outside. And I can explain here just briefly. So here the nuclei, here this is the nuclei, and I have here 2 electrons, and here these are satisfied, you see. And the last line, here I have 4 electrons which are not satisfied. Okay? So by these 10 electrons are called the electron of the Hertz. They are the closer compared with the others. And these one are the valence electrons, which are responsible to the bonds and everything else. And this is like the description we have done for the ionicity. This electron here, these electrons, should make bonds with other electrons with the same system. So another silicon could be here with the same description, and the last electron should stay here to make this satisfied. So I have 4 electrons. We need 4 to be satisfied for this layer. Okay, and so these electrons are attracted here. Okay, this is positive. Okay, to the nuclei, but they are pushed by these two. Because it will be like that, they will push them, so they will not see too much this attraction of the nuclei, which is positive. Here the charge is negative, this is positive. Okay, why? Because this electron will screen, make like screen, okay, to this attraction to the nuclei. Yeah? So this strong potential that I have will be removed partially with these 2 electrons of the Hertz. Okay. And consequently, what kind of interaction will I will have, or potential? It will be weak potential. In the beginning, it is strong. This is negative with positive, and this will remove this. Will push these electrons, and as a consequence, I will have a weak potential or pseudo potential. So this is to simplify this description for semiconductors, but the same idea for the other systems. Okay, so the most important things are just to remember this idea of pseudo potential, and from here we have to keep in mind that the most important electrons are those of valence, the last layer, because they are responsible of the electronic optical transport properties and the bonding also. They are responsible of the bond. Huh? Okay, and from here we spoke a little bit yesterday about Schrödinger equation. We said that we have to make a lot of approximations, because if we consider just 1 centimeter 3 of solid, it can contain maybe 10 power 23 of electrons. How can we consider all the interactions inside? It is quite impossible. So we have to make some simplifications. If we want to consider all the interactions in a given potential, we have to see the interaction between each electron of valence with the other one of valence, electron of valence with the one of inside, with the curve in the Hertz, and Hertz region with the Hertz region. Okay. Here in this description, you see we have kinetic energy parts with potential parts times the wave function equal to the energy and the wave function. The objective of pseudo potential method is to construct wave function like a plane wave, which is much more simple, and to have potential which is as weak as possible, according to description we have done. Okay, this was according to Phillips-Clement theorem. You can find this in Physical Review 1976. And we have this to consider this orthogonality between the wave function and the one of the Hertz. So the final description of Schrödinger equation will be this: kinetic part plus pseudo potential times the psi plane wave equal E psi or phi plane wave. Okay, we have this description for the pseudo potential. So we replace the strong potential going deeply by the other one. Okay, so the limitation of this method is that it was called in the beginning panacea, you know, like when you have a headache, you take one aspirin, you will feel better, but it doesn't mean that you are solving the problem. Okay, you can have other problem, just intermediate. But this was in the beginning, but because after that, pseudo-potential method knew a lot of evolution, and nowadays you can apply it in different systems, from semiconductors, metal interfaces, everywhere, even for the clay. As I told you, we have applied this method to solve several problems. Huh? So, but the limitation is that the empirical pseudo-potential, like the empirical methods in general, needs experimental data. If we don't have experimental data, we cannot go further. This is like classical molecular dynamics. Okay, the same. For atomistic methods, we need to fit the potential to some mechanical property like Birk modulus, elasticity, and so on. But here, we need to fit this pseudo-potential to gap, for example, energy gap. And after that, we have correct gap. It's okay. We can go further. We can have our band structure density of state at whatever you want. Okay. We cannot calculate the forces here, so we cannot relax atoms. We have to take the atomic positions as we took them from the literature, for example, or from X-ray diffraction, from experiments. We cannot relax and see which positions are the best, okay? Because we cannot calculate total energy, in fact, here. And the pseudo-potential he found is not transferable. What means that I have constructed pseudo-potential for zinc, as elements, it is a metal zinc. But if I put zinc with selenium, it is not metal, it is semiconductor. But the same pseudo-potential of zinc cannot be used for the case of semiconductor. We have to construct another one. And if I go to zinc oxide, which is ceramic, also it will not work. Okay, I have to fit a new one and find new pseudo-potential. So it is not transferable. It is not used in different situations. We'll see that for ab initio, it is like that. Huh? Okay, so I gave here some applications, the simple application, for example, for alloy system. I want to mix two different semiconductors. So I will vary the concentration, X. For example, when X equal 0, what I have? I have here, if X equal 0, I have ZnT, because this will be removed and this will be equal to 1. So the band gap, this is gamma gamma, you see? Gamma gamma. So the band gap, which is the energy needed to take, for semiconductors, to take one electron from valence state to conduction state. This is the energy. We don't have this band gap for metals, you know, because all this is free electrons. But for semiconductors, we have this band gap. It can be important. If it is too much important, like for carbide, then this is isolant. This is not semiconductor. If it is in like around 1 electron volt, then this is semiconductor, because we need just some external energy. It can come from just temperature, and then these electrons will be conductive, will contribute to conduction. So the band gap here is ZnT, X equal 0. It is something like 2.25, 26. The other extreme, when X equal 1, so X equal 1, so here I remove this. Okay? So I have Zn SE. over there. Okay, so the band gap of ZNSE is rather important. You see, it is around 2.8 over there. Yes, but in between what I have, you see, I have in one concentration around 0.3. The band gap is lower than the one of the two parents. Okay, you see, I will vary the concentration from 0 to 1, and I see that it will decrease till here, where the band gap is. Now it is something like 2.2 or even less. So, what I can predict here from this calculation, I can do this, for example, without any experiments, and can say to experimentalists, if you mix these two systems, you will have an intermediate one for this concentration, which will have a band gap lower than these two. Band gap means what? Means color, emission, and everything, optical properties. Yeah. So for industry purpose, people will like that. We'll see, okay, I will find, so I don't, because this band gap, it is a little bit huge for me. The other one, we don't want to hear about. So the intermediate should be very good for some application we want to do. So you give this information to industry, we just from calculation, and we are confident, we are sure that what we are doing is correct. You see? You see the goal from this, yeah? Okay. So here, well, the other gaps we don't care because we will not see them. The most important one is Dirac's band gap. You can also, for other situations, mix some different systems. One which has very good optical properties and electronic, with another system which has bad optical and electronic properties, but good mechanical properties. If I combine, for example, carbon with silicon, carbon has bad electronic properties, like this. Silicon with carbon. Okay? Silicon has very good, very important electronic and optical properties. Electronic, especially properties. This is the widely used semiconductor, you know, because it is very always found, you know, in silica. You can go everywhere with silica. Silica, this sand, yeah, it can be easily extracted. But if we want to improve the mechanical properties of silicon, we can make some alloy here in between, and we can find good concentration for which we combine good electronic properties with good mechanical properties of carbide. Okay, this can be done with such a theory. Okay, it's okay. And here, okay, this is traditional calculation of band gap. You see, this is, for example, the band structure of germanium. Germanium is semiconductor. We have all the band gaps. The valence gaps, because electrons we have, how many bands? We have 4. We saw from here, yeah. We have 4, okay, and each band can contain up to 2 electrons. This is the first band, second one, and third and fourth one are mixed. We see here this, yeah, but here they are mixed. And we see the band gap, for example, from here to here. This is little bit not really direct one. This is according to X. But this is difference between valence band and conduction band when the electron can exceed. So this is just small difference. with theory, we can have this band gap for all the system. And all system, all material, it can be metals, semiconductors, combination between, they have all their own band gap. This is like what I said yesterday, Nori was here. This is like a digital imprint. You see, everybody has his own one when you press, okay? So this is the same. Each material has his own. Not only for the band gap, also for the shape. We can see the effective masses here and so on. I'm not going to bore you with some further details. We can also speak about the bonding, even if this is not charge density. I gave the example of this here in X points. If we take carbon, we'll see that this band and the first one and second one, they're here, they're close at X points. For carbon, for germanium, silicium. But if I go to 3,5 compounds, here, because why? Because this is system is purely covalent. The contribution to the bond come symmetrically. But if I go to another system from okay, this is but for tails, so carbon, silicon, germanium, and even alpha tin or beta SN, okay? But here they have the same like that. But if I go to 3,5 semiconductor, like gallium arsenide, and with azote, so here I can see some splitting. Why? This is ionic system. There is the contribution to the bond will not be the same from this side and the other side. If I go to 2,6 compounds, the splitting which will be even more important. Okay, and so on. If I go to 1,7, I will see that here the splitting is like that, very huge. You see. So there are a lot of things about to speak about band structure. I give you here these two examples to see the prediction of the change of properties by including hydrogen in semiconductor, for instance. Hydrogen is very light element, and it can sit inside of sides. If I put hydrogen, what I will have here, I had the semiconductor. But here, this is not semiconductor. You see the bands come down, goes down, sorry, okay? So it is not metallic, because in metallic system, you will see the bands all like this, really random, okay? This is semi-metallic system. We don't have band gap. So we are changing here the property of this system, okay? So these are some predictions. The examples can be found in the literature. Oh, okay, no problem. Well, these are my own work, which we have done maybe 12 years ago or something like that. Okay. Now to conclude about this part of empirical pseudopotential, let me see. Let me say that so there are these two extremes, empirical, what we have done right now, and first principle or ab initio. You can find these two words in the literature, first principle or ab initio. What it means the same, okay? This means that the other extreme, that the study is done from the beginning. There is no need to experimental data. And here we need experimental data. And in between, there is semi-empirical, like science bending, semi-empirical method. And going from empirical to ab initio, we will increase the accuracy. It is much more accurate because there is no need to any experimental data. But of course, there is the price, which is the complexity, because we need much more time to handle the calculation, okay? They are all good. It depends what you want to do, huh? Okay, now let me recall a little bit density functional theory, what we have done yesterday. So density functional theory, it starts with Walter Kohn, okay, who got Nobel Prize of Chemistry, not physics, chemistry, but he was physicist. He was physicist, but they give him the Nobel Prize of Chemistry. That's this is always there is some politics, you know, everywhere, but life continue. Okay, so and he started. It's got a lot of success. He's still alive, and he's still in. I think in California. I think he's in US. Yeah, American guy. I met him once in Italy. Okay. But before he got the Nobel Prize, this method was widely used in Europe and in US, but maybe less in France. But once he got this Nobel Prize, because there is big information, everybody was interested by about this field. Yeah, nowadays you can find this field in everywhere in physics, chemistry, biology, metallurgy, everywhere, mechanics, you know. So, brief history. I said yesterday that from 1926 you have this Thomas Fermi extension. In 50 years, 60 Slater and co-workers, they developed CONSHAM local density approximation. The modern starts really in 1965, so a lot of times ago. And after that, it was developed. In 1993, a lot of other functions, we'll see about what this, we'll see the details, okay, was developed to have better exchange correlation. 1998, Kohn got the Nobel Prize with the guy who does this Gaussian program. It is mainly for molecules. Really, this is what I said yesterday. I don't, for Walter Kohn, I understand, but for Popper, not too much. It's just to make code, yeah. So to get Nobel Prize, well, but maybe because of him, of this guy, he translated this theory in code used. Everybody knows this method, and that's why he contributes for the knowledge of the method so much. 2008, dense functional was used now mainly for geology, soil science. Myself, I use it for soil science. I have some recent works in clay minerals like that, using the same theory. A lot of functional was developed, astrophysics and protein and so on. Okay. Here the same summary, but this is what I have done in different situations for my students. But it said the same about the density functional theory in the beginning with Walter Kohn and Sham. Here about the empirical pseudopotential, it was from 1959 to 1966, and after that Marvin Cohen developed very well this empirical one, and after that the development of LAPW and so on. Okay, we'll see what about this method. Well, to study a system in quantum level, you know this equation very well. We have to solve the Schrödinger equation, and after that we will get the wave function and the energy. And this resolution is not easy. We have to start with some approximations, the adiabatic one. What means that we have to neglect the movement of the nuclei. You know, the nuclei is compared with the electron, is very heavy. So the the size of the nuclei compared with the one of electron, you know that if we make bigger the nuclei, like the ground, this will the electron will be like the balloon of not baseball, even less ping pong. Yeah, you see, difference is huge, too much. So here we have to neglect these movements of the nuclei with, compared with the one of electrons. So like if the nuclei is stable in each in principle it's not stable, of course, but just to simplify. And after that, the development of Cohen-Sham. This is, to simplify, density functional theory. This is a functional of what? Of charge density. Okay? It starts with the variation and principle of Berg and Cohen. And the Cohen-Sham theorem states that this functional of a fundamental state, which is n of r. We'll see the equation. So, according to the theorem of Cohen-Hohenberg, we have the total energy, which is the minimum of the energy of the charge density. It has this development. So this first term is the one of kinetic part. There is no problem for this term. Here we have the potential between electron and ion. As I said, so we have to take into account all the interaction in principle. And this is complete one. Okay? So here we have a kinetic energy of a given electron. And here we have the interaction between an electron and the other ion. And here we have the electrostatic energy of Hartree between two charges. And the last one is the exchange correlation. What means exchange correlation? You see the electron will stay together without touching each other. Okay, they have to avoid themselves. And here they make there is some energy to, okay? And how can we describe this? It is very difficult because the oscillation here is very strong. You have, if you want to describe this movement with a schematic curve, it will be like this, very strong fluctuation. What kind of formula can you use to describe this? It is very difficult. You see, even if the energy here is very few, very small, but we have to take into account this because, as I said yesterday, we are doing physics, we are doing science, and we have to be accurate as possible. So these two terms are very important, and n of 0 is the charge density. Here you have the probability of presence of the electron in a special part of the space. Well, if we want to have more to write better this charge density, in principle it should be which n 0 de r. We have this is 2e, and here psi square. Okay. This is the we have to multiply by E, which is the charge, and 2 because the two possibilities of the electron. It has two spin, up and down. It can be do like that or like this. Okay, this is the much more complete formula, and of course you make your summation here on I and K, and here I, K. I is the index of the bond. Of the band, sorry. If you are in the first band, so you have to make your here in the first band and the second band, or all the bands what you want. And the K is the points of reciprocal space. You know, each real space has a reciprocal space. Okay, we speak just now about the reciprocal space. How can we approximate this? So, Schrödinger equation will be like this. The first time it's kinetic part. It is in principle P square over 2m, but you can simplify. You can take I, the complex one, equal to h equal to 1. This is another, right? You know this, yeah, about quantum mechanics. You know this, okay. Okay, so the effective potential will be this one. So electron ion, Hartree, and exchange correlation. Hartree, no problem. It is a simple equation. But for electron ion, we should make an approximation. For exchange correlation as well, we should also make approximation about that. So to solve the Schrödinger, the Kohn-Sham equations, we can follow this diagram here. So we start with a given charge density. It can be more or less random in the beginning. And after that, we have to solve Schrödinger equation. We have to diagonalize the matrix of Hamilton of Kohn-Sham and make a choice. Which one? Plane wave, that means we are in pseudo-potential case, or atomic orbital for the other methods. And after that, we will calculate the energy, the wave function. And once again, we calculate the total energy. We will compare with the one of the first. If it's okay, we calculate total energy. It's okay, we go to some other properties, what we want to do. And if not, we go back and we change till the convergence. This is the same idea like we have done for classical molecular dynamics and so on. We, as inputs, the theory is this. After that, this is technique. Technique is something else. We have, it come by experience. It is not for the first day we will understand everything, but just keep in mind the main ideas. After that, you have to practice, okay? It will come, no problem. And here, so you can fix, for example, convergence tests. You say that for this problem, I don't need to be very accurate, okay? 10 minus 5 should be good convergence test. Once the system, you make in programmation that if once this is difference is less than 10 minus 5, then it will stop. You calculate your total energy and so on, okay? So, but before that, before doing this, we have to make good choice. But what kind of approximation? Because everything is related to potential. We have here in this field, I say once again, two main things to take. So crystallographic, okay, and after that, it should be the approximation, the pseudo-potential, how each atom is interacting with the others and so on. And here, since we are in quantum method, we have two approximations to do with these two main problems: the exchange correlation and the electron ion potential. For the exchange correlation, there are a lot of approximation nowadays. I show here just local density approximation, LDA. This was the first one, but after that, as I said, the GGA, and just 3 years ago, some other functional which works better for clays, for minerals, you see. And here, for local density approximation, we suppose that the gas of electron is homogeneous, and then the electron density is localized in a sphere, okay, around, because the problem is what is happening in the size of the atomic sphere. It is like that if I have some fluctuation like that, how many, if I want to use a simple equation like the one of line, it is AX. How many, if I have a curve like this, how many lines should I use? Okay, I have to consider just portion like this one. I can know the equation here. I cannot know the equation for the whole. It is very complicated, but I can know just for local. positions. And okay, this is the idea of okay. Here the equation of exchange correlation, which depends on the charge density. Once again, for this approximation, you can find much more details in Perdue and Zunger paper, which was parameterized by the one of Ciperli and Alder. It was in the 1980 years. I cannot give you the, but it is easy. In Google, you put LDA, Perdue and Zunger, something like that, you will find the paper. We have to remark the following. So the LDA doesn't take into account the inhomogeneity of the charge density. In principle, sometimes it is homogeneous, but it is not the case always. Okay. Once we have an heterogeneity of the charge density, we have system which is composed with different elements, things like that. So things became more complicated, and of course this approximation became less accurate. The one of potential between the electron and the other ion. Okay, just one electron. How can this electron interact with the rest? Here, I will focus on two approximations. The one of pseudopotential that I mainly use myself, okay, and the one of LAPW, full that means linear augmented plane wave. So the plane wave augmented linearly, we will see here, and the same but with development full potential. So this is not full potential, this is pseudo potential, but here full potentials, okay? And also linear infinity orbital method, also it is very good, very well used, but in general scientists over the world, they use mainly these two, the pseudo or FP-LAPW. But I know several groups who are using, even in France, the group of Strasbourg, they use this. In Stuttgart also, Max Planck Institute. This was done by Oli Andersen. He's from the Max Planck of Stuttgart. And, there are a lot of groups over the world using all. For myself, in my group, we try to use pseudo, LAPW, and the other classical methods. Okay. Now, the pseudo potential, how it works. We have already an idea about the empirical pseudo potential. Well, this is the same for the pseudo potential correlated to density functional theory. The idea is the same. So we have to. Pseudo-potential method, the wave function is the one of the wave function of the Hertz, which will oscillate very fast. We are inside. This is the nuclei, electrons around. The oscillation will be fast. Okay, you cannot follow. So here we consider this, and outside we have the wave function of valence electrons, where the oscillation is less important. And here we can make the approximation as plane wave, which is A exponential A KR. This is plane wave. Okay, so you have this representation, the region of the Hertz and the one of valence. Okay, here we see the oscillations, but it is very simplified, you see. Huh? During the resolution of Kohn-Sham equation, the choice of the plane wave basis to describe the electron wave function needs a great number of plane wave to describe with maximum of accuracy the fast oscillation of the wave function inside of the curve or the Hertz region. Okay. However, the most physical properties depends essentially on the electron of valence, the outside electrons. These are, because these are responsible of the bonds, these last electrons will look to other atoms outside, okay? Okay? And from here we introduce, as we said before, the approximation of pseudopotential. The main idea here is this. So yeah, we have this strong potential because it is strong in the core region, okay? It's very strong. This part is this one. We are in this region, okay? It is very deep, huh? And we will approximate with this. Something like that, okay? And the same for the wave function. Here it is smooth, no problem. It can be well described, but inside, no. But we approximate inside because it is easy, otherwise how can we do? Okay, so with variation like this one, okay? So this is not a real wave function, this is pseudo wave function, this is not real potential, this is pseudo potential. But good approximation. There are some developments about those which make them as accurate as possible. So how can we construct the pseudo potential? Here also we have several methods. The pseudo potential with norm conserved, you know the norm. If you have to normalize every wave function, just to don't exceed number 1. This is probability of presence, you know. So the okay, the wave function, the real wave function, and pseudo wave function are more or less the same outside the core region, because this is smooth. This can be good approximation for outside, but inside of the core region, they are not the same, okay? And the generals of pseudo potential should satisfy this equation. You just have to read and to follow. Let me give you the good pseudo potential, or let me say the history of pseudo potential. So in 1979, Hamann developed one kind of pseudo potential. The same year, Zunger, Alex Zunger, and Marvin Cohen, American people, 1979. These are all published in Physical Review. And after that, in 1980, Kerker, he published this work in Journal of Physical and Doesn't Matter. And after that, Bashley and Hamann and Schluter in 1982, they developed a table of all pseudopotential for all elements. It's a Mendeleev table. You can just take them and put them in your code and works. Good development. The method of construction, and after that, David Vanderbilt in 1992, as far as I remember, he developed another one, which is very good, hard pseudopotential, which work good for complicated system. Like, for example, for carbon, we don't have a real core region because you have just few number of atoms. If you exclude the 4 of electrons, sorry, if you exclude the 4 electrons in the valence band, how many electrons will be inside? Just 2. So this was too complicated, but for the one of Vanderbilt works very well. In order to yourself, if you become one day specialized in these methods, you can think about developing some other approximation about that. It is not so. It is difficult, of course, but not impossible. Huh? Okay. So it's the best is to look for the weak number of plane wave. What means that fast convergence, because if you want a description of with plane wave is simple, but if you want to have a good description for this oscillation, you have to make great number. So which one is good? The one which needs just small number of plane wave to go fast for the calculation. You have to take in science in general about you have to take into account about the accuracy, but also the velocity of the work, the speed. How can, because life is limited. You cannot spend 10 years to have one result. This is impossible, huh? Okay. You are still very young, that's true, but life goes very fast, you see. So it is very important here. The transferability, pseudo-potential like this, from first principle, is transferable. So if I develop pseudo-potential for zinc, just for zinc, like metal, an element, the same pseudo-potential, I can use it to study the metal zinc, but I can use the same for the case of semiconductor, ZnSe, okay, with selenium. The same. I don't have to to develop another one, and I can use the same pseudo potential for this if I want to study the zinc oxide, which is ceramic. And for the case of interface, for any cases, the same one, if it is well developed, I will use this in different cases. So there is transferability of pseudo potential. It doesn't depend on the situation you will put this atom. You can put this atom where you want. It is well transferable. This is good point with this method. Huh? The pseudo-potential method ab initio give very good results for total energy concerning solids. However, the diagonalization of matrix sometimes it can be limited with the number of atoms. Why it is limited? You remember last week we were discussing about atomistic method. In atomistic method, we can go to some thousands. But here, why it is limited? You can go to 100, 200, it's okay. But it depends on the size of atom. If this is about hydrogen, we can go to maybe 300. It will be fast. But if we are considering, I gave the example of aluminium. Aluminium, how many electrons it has? 27. So think about this interaction between the electron and ion. How many interaction we'll have with one electron? 27. And so if I take 100 of atoms, it will be too much interaction. If 200 is too much, but for the case of atomistic, no, it is rigid, like balloon. It is just I neglect what is inside. You see, that's why. Okay, it is limited, so we can go nowadays to maybe 200 or something like that. For my case, we went to sometimes we go to 64 atoms, 120, 150. For some models of alloys, for example, or interfaces, you are obliged to increase. If this is just to see some mechanical properties, there is no interface, pure system. Just few atoms are okay. They represent the reality, the macroscopic state. If this is about doing calculation on interface, in order to reproduce the reality, you have to, you cannot take here from this side 10 atoms, 10 atoms. You are not considering all the interaction between this layer and the other interface. You have to increase a little bit to reproduce as accurate as possible the reality. Huh? If you want to hate the system like what we have done with classical, with atomistic, to make temperature, you are obliged to be closer to the reality, to make a huger system, a lot of tens of atoms, maybe 200, something like that. If you can do this with 500, then it's okay, but you cannot. Life is limited also. Okay. Before that, another approximation, which is related to the charge density. Charge density, as I said here, is the summation of this. So I make 2 for the spin. What? It's okay? Who? Yes. You do group theory? Oh, right. Yeah. You know, for the charge density, it is like that. You have to make summation on I, the index of the band. On K, this is a point of reciprocal space. For each real space, this matter, you know that, I have one reciprocal space. If this is, I have a system like this, here, okay, some atoms. Okay, how many atoms I have here? Just 8. But in the reciprocal space, if I make the diffraction, I will see what's happening. How many points should I have? Here I have, this is lattice parameter A. But in the reciprocal space I have A times A capital equal to 2P. So, if more I have large lattice parameter, I have the opposite in the other way. Huh? So if I have just small system, you know, how many points should I have? It could be an infinity of points in the reciprocal. This is not real space. It's just imaginary space, you know. Okay, but I can have a lot of points, some thousands, million, I don't know how many. Okay, positions, not atoms. This is not real. This is just fixed. But since I am doing here calculation based on charge density, what means on the reciprocal space over there, I have to make my summation on these k points, which are not a real space. The space I know, but they are from reciprocal space that I don't know. I have to make my summation of how many points. In the reality, several. So it can be infinite. I have to finish one day. Huh? Once. Oh, okay. So some people have done some approximation. The first one was Alfonso Balderetsky. As I said yesterday, this was my boss, supervisor in Italy, and he has done this approximation just to show that according to he has done some calculations in Physical Review 1973. He used the group theory, and he showed that in this reciprocal space like that, for example. I have here, for example, this is the center. It can be gamma 0, 0, 0, x 1 over 2, 0, and so on. But I have here too many points. He has shown that just 1 point, he calculated this, could be enough to represent all the others. Okay, just 1 point. Okay. So it goes very fast. If I have to make the summation on just 1 point, instead to do the Monte Carlo or something really maybe accurate, I will win a lot of time. You know, instead to spend several months, maybe I will do this in 1 day or something like that. Okay, but the accuracy, of course, here the difference between 1 point of Balderetsky, it is 2% from the reality, just 2%. So it is not too much, the error. If you want to make a choice between how many time you want to spend and between an error of 2%, it's better to have it. And Shadi and Cohen, so I think here the coordinate of this point is something like 0.6, 0.2, and maybe 0, but I'm not sure. It is in the paper. It is very simple line. Shadi and Cohen in 1973, they have found that 2 points, like they follow him, in fact. 2 points can be enough to represent the whole other points. But the accuracy here was 1% difference. So it is better in accuracy, but you will spend 2 times. Okay? But in 1973, Monkhorst and Pak, they have shown that 10 points can be sometimes enough, or you can generate yourself. How many points you should, K points you should use in your study. And you know what we do? Technically, here also there is theory, there is technique. You know, actually, what I suggest to my students to do in general, to make any calculation, we do convergence test. We start with calculation of, before doing any calculation about the property, I have to do total energy calculation. Before doing that, I don't know how many K points should be accurate. So we start with, for example, with 2 K points, okay? Okay, 2 K points. I make total energy calculation. This is total energy. Okay? I will have here 1 value. And after that, it will be 6 K points. I will have, let's say, another value here. And after that, I will make with the 2, with 8, with 10, with, I don't know, with 20. Okay? Okay? So here like this, and with 8, it will be something like that, 10, and maybe with the 20, I will have the same. Okay? When you see your curve, so between 10 and 20, it is the same. Why should I use 20 or 100 K points if 10 should be okay? So I will use just 10. Okay? And then we start to calculate. This way, this is called convergence test. Okay? Okay? We always start with this, with ab initio calculation, and then we cut. We have sometimes just 6 should be okay, without any penalty, and then we do our calculation. And sometimes a little bit more, we can go sometimes to 40 points, 50, and then it is really time consuming. But it depends on which system, which problem we want to handle, okay? But anyway, with these convergence tests, we save a lot of time like that, okay? So now, about another, this was pseudo-potential ab initio. Now it will be full potential, which LAPW. This method is called linearized augmented plane wave method. Okay, and here it is like the bee, you know the house of the bee, how to say honey give, okay? It is, we start to, if this is the atomic space, we try to fill all the space. Okay? Like this. Like what do you see? Okay, so, and here, as we have said for the case of potential, this can be represented with harmonic spheric, because this is like sphere here, this space, and the remaining problem is these places in between. This space can be represented by plane wave without any problem. Okay, and like this, I don't have pseudo potential, but complete potential, what we call full potential, all electron. Okay, so this is much more accurate. Not much more. It is more accurate than pseudo potential, but more time consuming. For we use this method as well, but it depends on the situation. In general, we prefer pseudo potential. For some cases, we do this one. So here, to sum up here, so the unit cell is composed into 2 regions. The first one is spherical atomic. The second one outside. This is interstitial region, the region in between. Okay. So in the two regions can be described like this: plane wave outside, interstitial region, and inside with a radial and a spherical harmonic inside of atomic sphere. This is just main idea to give you here, okay? But after that, this is technique. I can suggest you some papers like the one of Ole Anderson. It was published Physical Review in 1975. It gives all the data of calculations, you know, spherical harmonic and so on. And now there are a lot of codes using this, mainly the one of Vienne 2K. Well, the one of pseudo potential as well. Pseudo potential, you have. So for this LAPW, there is Vienne 2K code. So for FPLEPW, for pseudo potential, there is VASP code. Vienne is come from the city of Vienna, from Austria, you know, and VASP as well. It's come from the same city. This is FAPPW, and this one is concerning pseudo potential. There is also PWSCF. This is Italian code. There is also Abinit code. This is Belgium one. Well, there are quite a lot actually, you know. Which one is good? If your job is working well with one of these, then let it be. You don't have to make the. They can do the more or less the same thing. Okay. So let us sum up about the quantum method. So we have to solve this well-known equation once again, and the entire problem is how to modelize the pseudo potential in the Hamiltonian. We know that now. Okay. Here from this resolution we can get the eigenvalue as solution. From here we can go to all electronic properties, optical and also magnetic properties. The magnetic properties we have to include the spin, you know, instead to do, for example, as exchange correlation potential local density approximation, it will be spin local density approximation. So we can do density of states, for example, spin up and down, and extract magnetic moments, so on. We can do optical properties, which you can have dielectric function. This is the same, like what we have seen in band structure. The dielectric function will take into account all the transitions. Density of states which will be equivalent to photoluminescence system and so on. Okay, and so from this resolution, from here I get all these kind of properties, what I don't have with atomistic method. Okay, atomistic method, I can have some mechanical, I can have some thermodynamic and so on, but there is no electron, there is no optical, no electronic. Okay. And from here, psi, the wave function, and its square in principle, we can have good description of the nature of the bonds. Okay, because from the charge density, I will show you some examples. We can see what is happening, how the charge transfer can work, and so on. Well, the good point for the density functional theory is the good prediction for the fundamental states without excitation. What means that everything in the fundamental state can be well described. But once we are speaking about these transitions, it is less well described. It was at least in the beginning. Now there are a lot of improvements here. Okay, we had in the band gap, instead to have I don't know, for example, 1.5 electron volts, with the density functional theory, we'll have band gap maybe 1.1 or something like that. I'm doing mistake, but it is like that. Underestimate the band gap. But nowadays we can have with some good exchange correlation functions, we can have rather good value of band gaps or excitations. It was improved, but in the beginning, because it stays like this Cohen-Sham equation, it was based on the fundamental state, not excited state. Okay, this is what I want to say here. So from the total energy, we can go to everything related to structural properties, you know. This is what you can get from atomistic method. It is the same here. But the difference is that here we are doing ab initio, first principle. This is not classical potential, but really ab initio, ab initio. Some examples containing some studies using both pseudopotential and or LAPW. I show you. Well, production of structures at equilibrium. Here, this is the same what we have done with atomistic, but I have shown this with maybe zinc oxide. Here, the same you see in this system. It was not synthesized in the beginning. After that, people synthesized this system. So we have done this calculation, and we predicted that this system, indium with bismuth, can exist in that structure, and what properties will have, and so on. Okay, so this was good prediction here. You see the structure of the fundamental states, how it looks like from crystal quant of view, and here we took a lot of structure candidates, you know, Wirtzeit, Zincell, zinc blend, rock salt, PBO, and so on. And we calculate separately. Each time we will impose anatomic discrete positions for my system. It is composed with indium bismuth. I will put them like this, and I will change. Okay, in other structure, and I calculate the total energy for each case. Which one is the best? The fundamental one, which consists on the lowest total energy. Huh? We can also have some the same thing to see fundamental states, but instead to calculate total energy, we calculate the enthalpy. It is the same. We have the enthalpy, which is of the system, you know. It is total energy plus pressure and time volume. H equal E plus PV. And this is the same. But instead to have the curve like that, I can see the cross. Okay, the crossing. Because in the fundamental state, I am here at zero pressure. Where I am? I am here in this structure, zinc blend. And I see the evolution, the enthalpy. I will make the pressure. I will make the system denser, okay? Denser. And once the system arrives in certain value of pressure, the first situation is not appropriate. The atom will change, okay? The position, and it goes to another position which is much more appropriate energetically. That's the point. Huh? Okay, so I make pressure, so the energy will become higher. It's normal. Huh? It became high because the atoms try to avoid, and once I arrive here, it is around maybe 10 gigapascal, around more or less. Okay, the system will be forced to change, and it goes to another structure which is same. Okay, this is this is BBE bar with bismuth. The GMB is something else, zinc blend, and the pressure will be in another value here. And the same with aluminium with beryllium. These are not alloys, these are compounds. Alloys mean that I have to change the concentration, but this is stoichiometric. This is compound like this, fixed without any change of, there is no intermediate concentration. Okay. Band structure also, like what we have seen for the case of, let me say, of empirical. You see, you remember we were speaking about this splitting at X point. You see, for the case of silicon, it was like that, 1 point. And here we have splitting. That means that there is ionicity. Huh? And you compare this with the other one. If we go to 2,6 compounds, like zinc, selenium, this will be a little bit larger. That means that the system is much more ionic. What means that the ion is attracting charges much more, because the difference in electronegativity between the two systems is much important. When we separate, you take the Mendeleev table, column 4, and you go from the two ways, you will have the difference in electronegativity will be which will increase. Okay, so you see this splitting. It is, if we see now charge density, you will understand. This is density of states. She's charge density here. Charge density here. The maximum of charge is around what? Is around the ion. It goes from. If we take, I don't have here an example for the case of silicon. The case of silicon, you see the charge density. It is completely symmetric. You see something around silica here and something around silica here, the same. But here, this is not symmetric because arsenide is much more electronegative than gallium. Then, during the bonding, arsenide will attract electrons, will attract charge. Okay? This is the ionic system. And we can understand this from charge density, but we can expect this from the band structure X point. Here you can also construct the density of states of the system. If we want to, people doing experiment, they can do something similar. They can do what? They can calculate photoluminescence, which corresponds exactly to this, and you can compare. So you can predict this phenomena, which can be done experimentally from here. Okay, but theoretically, you can also see the contribution here for density of state for each atom, which amount, okay, which orbital is contributing more. I am not here all the details, but for this work, it was published maybe 5 years ago. We have shown a lot of indication concerning the percentage, which amounts was okay, orbital S, P, mainly, or D, or combination between them. Oh, this is concerning the interface here. I think it was published in 2004. That time I have done this alone. So this was, the motivation comes from an experimental study, okay, with the Japanese friend. He has done this work experimentally and tries. He didn't understood what he has found, you see. And I tried in that time to help clarifying the situation theoretically. This was what he has found here. This is experiment. You see, this is between palladium, which is a metal, with zinc oxide, which is ceramics. However, we cannot see what is happening in between. What we have, what termination, because you have a lot of possibilities, in fact, here. You have, you can have either oxygen here in front of palladium, because this is palladium 111 in 111 direction. Or you can have the zinc atoms in front of, at the interface. Okay? And because this is zinc oxide, in which structure is crystallized, it is in wurtzite. Okay, it is hexagonal. Hexagonal, you know, it is like that. You have this description. Okay. Even here, 2 bonds sometimes. Okay. And here you have this. Okay. So you have 1 atom here. Okay. 1 atom here, 1 atom. But which atom here, if I do this cut, this can be, for example, if the cut is here, this can be zinc, or this can be oxygen. We don't know. But we should know theoretically which one, because it is important for it. But if I do here this cut, here the bond will be just 1 bond, back bond. But if the cut is done here, in this place, I have 3 bonds, 3 back bonds, okay? And so on. So I can have either 1 back bond, 3 back bonds. I can have zinc at the interface, or oxygen. And also what I can have this atom, or this one, staying in, if I have here 2, suppose this is palladium atom, this is palladium. This can be in between this atom, but this can be in front of. Okay, the situation is different. Huh? This is called, if this atom is in front of, this called on the top. If it is in between, like here, this bond, palladium, and I have got on the bridge, and so on. Okay, or if it is, I have 1 atom here of palladium, 1 atom here, 1 atom here, and the other one of zinc or oxygen come like this. It is in the hole, like this. Okay. So experimentally we cannot see that, but theoretically we can explain that, and this is the power of theory, if you want. Huh? So these are the possibilities what we are speaking now. So this is, I can have this succession of palladium 111, A, B, C, A, B, C, and so on. And in the other side, I can have either, as I said, zinc or oxygen. But I can have displacement on the top, on the bridge, FCC hollow, HCP hollow, and so on. A lot of possibility. Which one is okay? Before that, we start with some studies here. It is important to see a mechanical point of view. I don't know if, which interests for you, which is more interesting. But here we can see how can the atoms can, or the lights can accommodate at the interface. So we will see the energy of the bulk or of the slab, a lot of atoms. If we can press them and delete them and see this energy for the case of palladium 111, the same for the case of zinc oxide. Here we see that the different energy difference is not so huge for the lateral strain. So the 2 systems can accommodate as the interface with more or less the same effort, you know. Important quantity that can be measured experimentally is the one of energy of separation. It is calculated in experimentally with joule over meter square. Here the situation is like that, because when you put, you have palladium, and after that, theoretically you have to put, for example, zinc. But where? Which? In the same expected position of palladium, or a little bit far, or you don't know also the place. Okay, so we calculate here this work of separation for the different situation, 2 interface separation, palladium, and so on. We see that this is the best place at the distance between is more or less this one, okay? And this is like the one of Coulombic part. If we separate palladium with zinc oxide too much, no, if we try to make them too short, the energy will be high because they try the two systems to push themselves. It will be high. And if we separate them too much, you see, we go to zero. It is, as I said last week, it is the situation if palladium is here and zinc oxide is outside. There is no interaction between them. And which one is the best distance is in between. Okay? Distance between palladium and zinc oxide, this can be calculated. Huh? So this is what was found experimentally, but we cannot really occur. These are, I put here my point, my finger, but experimental, they saw only this. So how can we expect that this should be the situation? This was done theoretically from the slab I will show. So you see palladium 111, and after that you have 1. And also, but this is not always the situation. It can change a little bit. Huh? So I show here that the situation is different for the two interfaces. We have two. Huh? Well, these are what we have done theoretically, pure, okay, and expectation from our ab initio calculation, pseudo-potential calculation, also for this. Huh? IDP here, just I wanted to show you that this situation can exist. This is hexagonal case, but in principle, this repetition is like that. You have this atom, and here you still to have in front of this one a red one. I have green one. Okay, this is a defect in structure, but I use this defect just to do my calculation. I force the system to have these defects because otherwise I cannot find the final energy. You see, this is. But you have to know that this situation can exist in a lot of hexagonal systems. From the density of states, also we can see the contribution to the interface from zinc and palladium and oxygen, different orbitals, and we see what is happening at the interface. Okay, for the case of bulk zinc, oxygen with p orbitals, and so on. But it is much well described if we see Char density, net Char density. You can see especially here what is happening at the interface, this charge transfer between palladium and zinc, how it looks like. You see the highest energy, charge density, okay? And you can also recognize the, I'm sorry for that. This comes from France, I'm sure. Okay? I'm sorry, I will just close my phone. Nobody will call me. How many times has it? Huh? Yeah, 15 minutes is okay. Huh? Yeah. I hope that I don't bore you. It's okay? Okay. So the charge transfer. This cannot be done with atomic method. With quantum, you see the charge density, you see the charge transfer. How the interface can exist? Why it can exist? How can it can be stable? And you see, this can be explained and can be understood from here, from the charge density transfer. Okay. I want to tell you something else. Okay, right now what we have seen. We have seen atomistic methods we have seen quantum methods, empirical one, and ab initio. For the quantum methods, this means in the electronic state. But what I want to tell you that we can also use quantum method, but instead to consider electron, we can consider positron. How it works, okay? Here, experimentally, I will start with experiment, and I will explain you how can we jump from experiment to theory with positron. Well, from experiment, we have this interaction between positron and the matter. How it works? So we have, they take people. I have never done this experiment, you know. But people can take some isotope of sodium, and they can create positron. And this positron is just one. Every 10 minus 11 seconds. Just one positron, which will come, which goes to the matter inside. And the life of this positron is like that. If I don't mistake, maybe also 10 minus 11, things like that. So, or minus 10, I'm not sure. Okay, but before the other positron come, the next one, the first one already died. It already disappeared. How this positron can disappear? Okay. This is, well, positron first, it is like electron, but in positive charge. This is not like nuclei. It has the same, well, not the same characteristic, more or less. I always tell to my students, this is like positron electron, it is like man and woman, you know, the same more or less characteristic, but with some differences. This is like that, just question of charge, you see. And so positron is like that, like electron, but it doesn't exist in the matter. You are working, electron is everywhere, but positron you will create. You create from the source of sodium, it goes to the matter. And once it is inside of a solid, it will disappear. How it can disappear? It will either meet an electron. If the positron meets the electron, they will make some radiation, gamma, and then the positron will disappear. There is no positron. And sometimes, before it meets an electron, charge, I mean, an electron with negative charge, it goes to some hole, some defects. So instead to disappear, it will take a little bit of time to meet the electron. And we understand from here, even if the time difference is not so big, that there is defects inside. There is some problem. Okay? Or dislocation or something, a lot of kind of defects, but it's come by experience. People working on this field, they can expect, they can say that with some knowledge that there is what this kind of defects, where, and so on. Okay, so and after that, so it will be blocked in one hole inside of the matter, and after that it takes just few, not second, very few time. After that it will meet an electron and it will disappear, creating gamma ray or something like that. Okay. But it is very important for our information about the defects in a given system. This can be in semiconductor, in metals, in interfaces, in I don't know, in for the things like minerals. I don't know. Okay. So the possibilities here of positron is like this. We have positron which come. This is the interface of the matter. And after that, it's enter. We can have a lot of possibilities. And these possibilities are like this, okay? we can have this kind of positron. This it can diffuse, but this is the main thing for us. Okay, it can be captured with some defects, and its lifetime will increase a bit. Okay. After that, for sure, after a certain time, very few time, it will meet an electron. So electron plus potassium, it will be annihilation. Okay, it will be removed. Removed how? It will create two gamma rays. Okay, like this. But this difference of time will tell us about the situation of the matter we are considering, how it is, and so on. Well, this is from experimental point of view. Now, from theory, can we do that? Yes, can we do that? The same, you remember this Kohn-Sham equation, you can add just one term indicating the interaction between the positron and the potential of positron with the other particles. This is called IPM, independent particle method, which is not free electron, not free particle. This is not free, independent. Why this is independent? Because I never have the same particle at the same time. I have just one positron coming from here, going to the matter. And once this positron will die, the other one will come. Okay, because the lifetime of positron is very fast. And before creating the second positron, the first one is already gone. Okay, so I have the interaction between this positron and the whole of the matter. But I don't have the interaction between positron and positron. Okay, so this can be done theoretically, as we said. Okay, and in some other situations, of course, we are not going to. This is at least 3 or 4 lectures itself. I'm not going to tell you a lot of details, but there are in some situations we can have some positron can be back. You know, with the slow positron, with the pseudo things like that, you know. But the main thing is the other one. So, some overview concerning experimental technique about positron. You have here this diffraction of positron at low energy, LAPD, between 0 and 300 electron volt. And the other one, spectroscopy of annihilation of positrons. Theoretically, as I said, we have electron charge density, but we have positron charge density, and this can be included in with the pseudopotential method, with the IPM. Okay, here just an example, and I finish. The interest of positron, we can know the defects in the matter. This is important. For this case, we have done this study maybe in 1999, 98, I don't remember exactly. To see the lifetime of positron for several cases, you see. This is theory and this is experiment. And you see the difference is very weak, really, the lifetime, even if it is very few. Okay, and then we can understand, for example, for the case of alloy, which is, of course, there are defects in alloy. How can we understand defects in such alloys through positron theory? Okay, so well. I want to say here just a few words concerning the importance. So the importance to use this theory. I want to also to say something else concerning the bridge between molecular dynamics and ab initio, but we don't have time. This is at least 1 or 2 more lectures, but you just keep in mind that it exists. With ab initio, with molecular dynamics. Instead to have the atoms to move like rigid one, we will have the particles moving, and it is also really time consuming, but we use it one day for different situations. So we have done right now classical, atomistic, quantum, and we have the bridge between them, classic molecular dynamics and ab initio, okay? And all this theory can be applied for several situations, as I said, in biology, and I don't know, for electronic, for everything. Just to be careful, how can we use them? How, in which situations, and that's all. And after that, in principle, it is, can be applicable everywhere. Yeah. And this is theory. You are not doing experiments. If you need just one thing, you are stopped for 1 month. It depends on you. Okay, just your computer and papers. Okay. Thank you. Do you have any question?